We have been studying the motion of a particle in quantum mechanics, and we have found that a particle has to be described by a wave psi xt or psi r and t, where psi is a function of the position and time, and the evolution of this wave is governed by the Schrodinger equation, which is shown here, and the interpretation of this function psi is in terms of the probability, where the mod square of psi is the probability density defined in such a way so that the mod square of psi, or the probability density into the volume element dV, gives us the probability of finding the particle in this volume, in the small infinitesimal volume dV, located at the position r, where r is this function, the argument of the function. So this gives us the probability of finding the particle here at some time t. Now, so this wave function describes one particle, and we have only access to the probability of finding the particle, the information about the probability of finding the particle somewhere. But whenever we make a measurement, we will always find the particle at one point, not distributed. So this is about the information as to the position of the particle. Now you may be wondering, what about other dynamical variables? For a particle moving in a potential, you may measure, say, the momentum, or you may talk about the energy or angular momentum. There are many other dynamical variables which you can measure in classical mechanics. How do we deal with these in quantum mechanics? For position, I have told you how to go about dealing with it, right? All the information about the position is in the wave function or in the probability density. Now, if you want to deal with the other dynamical variables, so then we have to, in quantum mechanics, all the dynamical variables are represented by operators. So this is another, you may say, axiom or postulate of quantum mechanics. In quantum mechanics, for every dynamical variable in classical mechanics, in quantum mechanics we have in quantum mechanics what we have is a Hermitian linear operator. So I shall be explaining to you shortly what is a Hermitian linear operator, but let us get the postulate clear first. The postulate is that for every dynamical variable in classical mechanics, there is a corresponding Hermitian linear operator in quantum mechanics. Okay, so and there is a bit of loose notation here. So in classical mechanics we have, let us say, the position of the particle. So we have x, we have y, we have z, or the vector r. In quantum mechanics we have correspondingly some operators. So this is classical mechanics, this is quantum mechanics. We have some operators which may be denoted by, which are denoted like this. So x, y, z here refer to the position of a particle. we use the same symbol x, y, z to denote operator, the corresponding operator, except that we introduce a cap on top, or hat. We introduce a hat on top. So x hat refers to the operator corresponding to the position of a particle. Y hat is another operator, z hat is another operator. These operators somehow correspond to the x, y, z position of a particle in quantum mechanics. How it corresponds to the x, y, z position, we shall be learning slowly. Similarly, we have px, py, pz momentum, and here we can have operators px, py, pz. And we have energy, or we have the angular momentum Lx, Ly, etc. I shall also be using a notation like this, that the operator corresponding to a vector r shall be denoted like this. So this is just the notation that we shall be using. The hat on top indicates that it is an operator. It is no longer just a quantity like x, no longer the argument of a function, or no longer a quantity x, but x with the hat is an operator. Now what is an operator? What is a linear operator? Let me first tell you what is a linear operator. So a linear operator maps a function to another function. An operator maps a function to another function. So let us take an operator A, some arbitrary operator. This will act by some means on some function psi of x, and this will give me another function phi of x. So let us look at a few examples of operators. So one operator, linear operator, is the operator x. The operator x acting on the wave function psi of x, or on any function psi of x, gives me a new function which is x into psi of x. So let us go through this again. The operator x acting on this function psi of x gives me a different function which I may call phi, and phi of x is equal to just x into psi of x. X into psi of x is a function which is different from psi of x. So this is one example of an operator. What do we mean by linear operator? A linear operator has the property that if it acts on A, where A is some complex number, into psi of x, plus B into, so let us replace this by any arbitrary linear operator A, phi of x, this is equal to so the action of the operator on any linear combination of two functions. By linear combination I mean you can multiply one function by a complex number, multiply the second function by another complex number, and add them. This again is a function. The operator A acting on this function is equal to this number here multiplying the operator A acting on psi plus the number here B acting on the function phi, Okay. So this is what is meant by linearity. Will there be a hat on what? On
the right hand side.
There will still be a hat. A is still an operator. Okay. Now all that we have is that A is or you can, let us take a simpler case where A is acting on psi plus phi. This is equal to A acting on psi plus A acting on phi. If A is a linear operator, it satisfies this. It also satisfies A acting on some constant into phi is equal to the constant into A acting on phi. And here we have put both of these properties together and we have this. Okay. So if A is some linear operator, it satisfies these properties. It has these properties. So this is what we mean by linearity. Now let us go on to what we mean by Hermitian. So before we can understand what is meant by a Hermitian operator, Hermitian linear operator. So all the operators we are going to talk about now and in the rest of the course are going to be linear. So I shall not explicitly say that an operator is linear. It is assumed. So let us now go on to define what we mean by a Hermitian operator. Before defining what is a Hermitian operator, let me first define what is the adjoint of an operator. So the adjoint of an operator A is denoted by, so this is adjoint, the adjoint of A is denoted by A with a dagger over here. There is a dagger, so this upper part is smaller and the lower part is bigger. The adjoint of A is denoted by a dagger. So it has a small dagger on top which indicates the adjoint. How is the adjoint defined? In order to define the adjoint, we have to then now define the inner product of two functions. So let us look at the inner product. So the inner product is being defined, is being introduced to define the adjoint. The inner product is something very useful. So let us suppose that psi and phi are two wave functions corresponding to two different kinds of motion of the particle. For example, the particle may be moving with a momentum p1, that will have some wave function. Particle moving with the momentum p2 will have a different wave function. Let us call that phi. So phi psi of r and phi of r. I am not showing the t explicitly, but the t is there, and the same instant of time t appears in both of these. So the same t appears here and here. So psi of r, let it correspond to one state of the particle. Phi of r is a different wave function for the same particle. So a particle may have different kinds of different motions which have correspondingly different wave functions. So these are two different wave functions for the same particle. The inner product of these two functions, which is defined to be minus infinity to infinity psi star r phi r dv, where this integral is over the whole volume, the whole region of space over which the function is defined. If it is one dimension, it will be a one-dimensional integral. If it has some limit, some finite range, then it will be, has to be imposed. So it is over the whole range over which this function is defined, and this is denoted in short by this. This is some notation that we shall use. So this is the inner product of psi and phi.
So can we reverse the terms?
Well, the question being asked is, can we reverse these two terms? So let us see what happens if we reverse the two terms. So if we reverse the two terms, that is phi and psi, then this is equal to minus infinity to infinity. Now I have phi star r and I have psi r dv, which you can see is different from this over here, but the relation between these two is very simple, and this is equal to nothing but psi phi star. So if you reverse these two, which is what we have here, you get an extra complex conjugation. Or the inner product of psi and phi is the complex conjugate of the inner product of phi and psi. So we have an inner product, we have defined what is the inner product. This may appear familiar to you because the inner product of psi with itself, of a wave function with itself, is this integral psi star r psi r dv, which, if you recollect, should be 1. Why should this be 1? It should be 1 because psi star into psi is the probability density. The total probability of finding the particle somewhere has to be 1. So this is the total probability of finding the particle somewhere, and this is 1. A wave function is said to be normalized, so this is called the normalization, and a function psi is said to be normalized if it satisfies this. So this is called normalization. And psi is normalized, or it is a normal wave function, if it is, its inner product is unity. Okay. Now let us go back to what we mean by the adjoint of an operator. So I hope you're all with me till now. We have defined the inner product. We have defined what is a linear operator. Now we want to define the adjoint of an operator. So the adjoint of an operator is defined as follows. Let us first consider this. So the operator A acting on phi this is a wave function. I can take the inner product of this with some other wave function psi. So let us put that here. So this is the inner product of two functions. The first function is psi. The other function is the operator A acting on phi. This is the inner product of these two functions, which is, this is what is shown here. Now the adjoint of A is defined as follows. Let us look at this. So this is the definition of the adjoint of A. Let us look at this definition a little carefully in order to get some understanding of it. So here A is acting on phi. and I'm multiplying it by the complex conjugate of psi, and then I'm integrating it. Now, the adjoint of A is defined as an operator to be some operator which acts on psi. The psi appears here. Here, the adjoint of A acts on psi, and then I multiply this by phi star. I integrate this over volume, and then I take the complex conjugate. So A dagger is defined so that this is equal to this. A dagger is defined in such a way so that this quantity is equal to this. Or in this compact notation, this second term here, the second line, is equal to phi A dagger psi star. So let me again go back to how the adjoint is defined. The adjoint is defined as follows. Here I have A acting on phi, and then I'm taking the inner product with psi. I want to define another operator which acts on phi. Sorry, A is acting on phi here, so I want to define another operator which acts on psi. The operators act on anything that appears on the right hand side. So in order to have another operator acting on psi, I have to move psi onto this side and phi onto the other side. This will involve a complex conjugate, and the new operator A dagger is defined in such a way so that A dagger acting on psi inner product with phi complex conjugate is equal to A acting on phi inner product with psi. Let us calculate the adjoint of one or two operators to get an understanding of what this process is all about. So let us okay, before that, let me tell you what is a Hermitian operator. A Hermitian operator is a self-adjoint operator. This implies so if an operator is equal to its adjoint, so if A is an operator, A dagger is its adjoint, if the operator is its own adjoint or if it is self-adjoint, it is called a Hermitian operator. So for every dynamical variable in classical mechanics, in quantum mechanics, there is a Hermitian operator, and this is what a Hermitian operator is. Now let us look at a few operators and see if they are Hermitian or not. Okay. So we have already talked about one operator which we defined, which is X. We want to see whether X is Hermitian or not. So how do we go about seeing whether X is Hermitian or not? So we have to first look at this quantity, which is phi x psi, which is equal to minus infinity to infinity phi r x acting on psi r dV. Now we know what is the action of x on psi. The action of the operator x on psi is to give us a new function which is just the variable x into psi. So this integral is, there should be a complex conjugate here, is nothing but minus infinity to infinity phi star x into psi into dv. So let us go back again to what we were doing, what we are trying to do. What we are trying to do is, we are trying to see whether x is adjoint, self-adjoint, or whether x is Hermitian or not. In order to do that, we have to act with the operator x on some function psi and take the inner product with phi. This is the quantity we have to look at, and this follows from the definition is equal to this integral minus infinity to infinity phi star x acting on psi. Now x acting on psi, I have already told you, is just the variable x, the operator x acting on psi is just the variable x which refers to the different positions multiplying this function psi. So this is a new function. This is a new function which is this operator acting on this function. This multiplied by the same old phi star integrated over volume. Now in order to find out the adjoint of x, we have to get an operator which acts on phi. How to do that? So this we can write to be equal to minus infinity to infinity psi star x phi r dv, the complex conjugate of this whole thing. So this is equal to this integral which we had, because the complex conjugate of x is x itself, and the complex conjugate of psi gives us psi, the complex conjugate of phi gives us this phi star. So this is equal to this. Now this is nothing but x acting on phi so this integral we can write as follows, that so what have we obtained? We started out trying to simplify this phi, inner product of phi with x acting on psi, and we find that, so we are simplifying this and we find that it is equal to this, which is the inner product of psi with x acting on phi, the whole thing complex conjugate. Now let us look at the definition of the adjoint. So let us go back to the definition of the adjoint. So the adjoint of A is defined as follows. So if you have an operator acting on phi in a product with psi, and if you can express the same thing here as some operator acting on psi in a product with phi, I have interchanged phi and psi with a complex conjugate, then I know that this operator which appears here is the adjoint of this operator by definition. So let us look at this. Let us look at this. So we started out with x acting on psi in a product with phi, and we have shown that it is equal to x acting on phi inner product with psi complex conjugate. So this implies that the adjoint of x is equal to x, because this is the definition of, so this is also equal to psi x adjoint phi star. This is how the adjoint is defined, and we have shown that this is equal to this, which indicates that x is the adjoint of itself. Now let us look at another operator and try to see if it is Hermitian or not. So x is a Hermitian operator. X is a valid, this operator x defined, which we have defined, is a valid candidate for an operator to be to represent a physical dynamical variable, and this is this operator represents the position of the particle. Now let us look at another operator which I can call d. Let us call it dx, and dx is defined to be del x. Let us see if this operator is Hermitian or not. So how do we go about doing it? We follow exactly the same procedure. So we first look at this, the inner product of dx with, so dx acting on psi inner product with phi, which is equal to minus infinity to infinity phi star r, the partial derivative with respect to x of psi. So this is how this left hand side is defined. By definition it follows that this is equal to this. Now we want to get another operator which acts on phi. How do we get this derivative, the partial derivative acting on psi, to act on phi? Well, we have to proceed by doing an integration by parts. So doing an integration by parts, this can be basically written as follows: minus infinity to infinity del x of phi star r psi r dv minus this x. So this will have two terms. One term will be the derivative acting on psi, which is what we want. We will have an extra term which is the derivative acting on phi, which we don't want. So we have to subtract that out. Minus infinity to infinity, the derivative acting on phi. I am not showing the arguments explicitly. In psi, phi star psi dv. So this is equal, the sum of these two is equal to this, right? Because this will give you two terms, one of which is cancelled out by this, and what we have remaining left is the integral we want. Now this integral can be done. If you do this integral, the dv integral has got three integrals inside it: dx, dy, dz. So the integral over x, if you do the integral over x, this is a derivative with respect to x alone. So if I integrate over x, what I get is this function, this integral then becomes this function psi star r into phi r evaluated at x going at minus infinity and x equal to infinity. Because I can do this integral over x. So if I do integrate over x, this derivative will go away. I will only have this function dr at the two limits. I will still have the y and z integrals left, and I have two more integrals, minus infinity to infinity dy dz. Now the wave functions are defined in such a way so that they fall off at infinity. Or the particle we know is within some region. It doesn't, the probability of finding the particle at some very distant place is 0. So this function, this integral is 0. This is just 0.
Is it psi star or is it phi star?
It is phi star, sorry, I have interchanged them by mistake. So let me correct it. This should be phi star and this is psi. The same thing here. Okay, so we can drop the first term and we are left with only the second term, which is minus, then we have the limits of the integral, then we have psi. I am just interchanging the two terms. We have this, and there is a complex conjugate here, and this is equal to minus of the integral from minus infinity to infinity. Then I have psi star del x of phi dv, the whole thing complex conjugate. So we find that this is equal to the minus the inner product of psi d x phi. So what did we start out with? We started out with phi inner product with psi So we started out with phi, the inner product of the operator dx acting on psi with phi. This is what we started out with. After doing some integration by parts, we see that this quantity, this is equal to this, the complex conjugate of that, right? We also know from the definition of the Hermitian, the adjoint, definition of the adjoint, that the adjoint is defined as follows, that the adjoint is a new operator called d dagger, and it is defined so that this is equal to this. Now if we compare this with this, we find that the adjoint of D is equal to minus D. Right? So this operator is an operator which is not Hermitian. Well, this operator has a special property, it is anti-Hermitian. Anti-Hermitian. So if an operator is its own adjoint, it is called Hermitian. If an operator is minus its own adjoint, it is called anti-Hermitian. You can have operators which are neither Hermitian nor anti-Hermitian. Okay. These are two special, but Hermitian and anti-Hermitian are two special kinds of linear operators. Now, I leave it to you to check that I into this operator, that is where I is the square root of -1, to check that this is Hermitian. So you have to repeat the same exercise and just use I into dx instead of dx. So this operator where I into this dx, which we were dealing with till now, this is Hermitian. So we know now what are Hermitian operators. We know the condition which it has to satisfy. So in quantum mechanics, we use Hermitian operators to represent dynamical variables. So in classical mechanics, we have a set of dynamical variables. When we go into quantum mechanics, we have to introduce operators to represent these. Now, what is the operator corresponding to momentum? So we already know what are the operators corresponding to position. So corresponding to x, we have an operator x whose function I just told you how it acts. Similarly, for y we have a corresponding operator. For z we have a corresponding operator. So x acting on psi r will just give me x, where x is the argument of this function, into psi r. Similarly, we can have y and z. Now, the operator corresponding to momentum is minus I h cross del by del x acting on psi. So this, the operator corresponding to momentum, that is P, is minus I h cross del by del x. We can put, this is Px, the x component of the momentum. Similarly, the operator corresponding to the y component of momentum is del by del y, and the z component of momentum is del by del z. We can put all of this together and indicate it like this. The operator corresponding to the vector momentum is equal to minus I h cross times this nabla operator. And we just saw that this partial derivative is an anti-Hermitian operator. It is very easy to check that I into the partial derivative is Hermitian. So this is a Hermitian operator. It is also a linear operator. We all know that differentiation is a linear operation. So this is the operator corresponding to momentum. As we go along, we shall introduce the operators corresponding to other dynamical variables when needed. Now, let me also tell you how you can represent in the most general way how to represent an operator. So suppose O is an operator. Let O be some operator which acts on psi to give some function phi. We can represent that operator O through its kernel. So what is the kernel of an operator? So the relation between phi and psi can be expressed through what is called the kernel of O in this fashion. So we want kernel of O, which is a function of r and r prime psi r prime dv. So any linear operator can be represented in this fashion, where k, this quantity k, which is a function of r and r prime, is called the kernel of O. how do we get the function phi from the function psi? Through this kernel. The kernel is a function of two arguments, r and ir prime. So we have to take the function psi, which is being mapped to the function phi by the operator, multiplied by this kernel, and integrate over r prime. So this will give us phi at the point r. And this is the most general way of representing a linear operator. Let me give you one example of writing an operator in this way. The example may appear quite trivial. So let us look at the situation where the kernel is a Dirac delta function. So let us consider a situation where we have an operator O whose kernel is the Dirac delta function. So what happens when O acts on a function psi? So we have to look at the integral minus infinity to infinity. Then we have the Dirac delta function here. And here we have psi r prime. Now the Dirac delta function has got value 0 when r is not equal to r prime. When r is equal to r prime, the value of the Dirac delta function is infinite. And the Dirac delta function is defined in such a way so that this is equal to psi r itself, the same function at the point r. Right? Because whenever these two are different, it is 0. This function, the kernel is 0, or the Dirac delta function is 0. The cube over here indicates that there are three Dirac delta functions here, one for x, one for y, one for z. So when x is equal to x prime, y is equal to y prime, z is equal to z prime, then this function is infinite, otherwise it is 0. And the function is defined in such a way so that this integral is equal to the same function itself. So can you tell me the operator for which this is the kernel? The answer is very easy. It is the identity operator, because it maps a function to itself. Okay. So let me just very briefly recapitulate. So today I have told you that for every dynamical variable in classical mechanics, in quantum mechanics we have a Hermitian operator. Now, how do we go about making measurements? Suppose we have an electron, we can measure various dynamical attributes of the electron. We can measure its momentum, its angular momentum, various other things. So how do we mathematically model this using these operators and wave functions in quantum mechanics? We shall get into in the next lectures. Okay, I shall end here for today.